Today we study ESA23H, understanding a straight line. We search for the shortest curve that connects the 2 points in space in the three-dimensional Euclidean space, so A and B. We can always choose an appropriate set of Cartesian coordinate axes so that A and B are placed on the x-axis. So this is x-axis. This is a straight line connecting A and B. For simplicity, we can choose this A to be the origin of this Cartesian axis and choose B on the positive side. Then any point on a plane, we choose an xy plane. For simplicity, we convert this problem into a two-dimensional case. So let the curve connecting A and B. The starting point A to the end point is B, and the curve is on the xy plane only. Then we can measure the length of this curve and would like to find the shortest path connecting A and B. Everybody knows that the answer is the straight line connecting A and B. But we would rather choose a stupid way, but it is a very rigorous way to verify that the shortest path connecting A and B is a straight line. It is true that, for example, I have 2 points, but I can choose a point C and we can draw a triangle and we can apply the Pythagorean theorem. Then the path, this hypotenuse is greater than this side. Again, this hypotenuse of this right triangle is greater than this side. As a result, the straight line connecting A and B is longer than this broken path AC plus CB. But it is only for the straight line and the broken lines. We would like to generalize this idea to a more general case, that is a curve. It's not a connection as broken lines, right? No, not at all. We'd like to find the smooth curve. Among the smooth curve, the straight line is the shortest path. Okay. To do that, we'd like to define the length of infinitesimal line segment connecting x comma y on a curve, on the curve that connects A and B, and we choose another point is slightly shifted from the point x comma y. So that is x plus dx of y plus the dy. Then we can find a triangle. This length along the x-axis is dx, and this side, the vertical side, has the length of dy. Then, if the 2 points are infinitesimally close to each other, the length of the hypotenuse will be the value dominated. This very close enough converges to the length of the line segment. The curved line connecting the two infinitesimally close points is nothing but this value. We have applied Pythagoras' theorem. Why don't we factor this dx? This is a positive definite along the 0 and positive point whose x-axis Cartesian coordinate is x. So we can factor this differential length element along the x-axis dx out. then we can take the ratio of dy and dx. What's that? This is the slope of this hypotenuse, and actually in the infinitesimal limit, that is the first order derivative of the function represented by representing this curve, f of x, y equals f of x. All right. So the initial position for xa, that is actually 0. The final value is xb. From 0, that is actually xa, it's 0 to xb, we must integrate the square root of 1 plus the derivative of this curve squared. All right. Why don't we define this? This is the integral of differential. Why don't we rewrite this one? This x coordinate is to be replaced with t. Right now, we forget about the time. Time t, it is just an integral variable. Scale is integral, dimensionful integral variable with the dimension of length. So dt, we just replaced x with the t. And why don't we call this square root function to be L? Later, we will define this one. In case we study classical mechanics, equation of motion, Newton's laws of motion, then we will call this function L to be the Lagrangian and S to be the action. But right now, just a function, function L, and that this function is a function. This function depends on the path, shape of the curve. And f is now replaced with x. So here x is replaced with the t, and f is replaced with the x. Therefore, this first order x derivative, and actually first order df over dx has been replaced with d x of t dt. Okay? We vary the path keeping the two endpoints the same, and we'd like to choose a curve, and then from that curve we deviate the curve. So why don't we use another color? Okay, so this is represented by the curve x of t. Now we call this horizontal axis to be that time axis, something like that, t, and this curve is represented by function of t that is called x. Okay, so we vary the path from this. So this one is replaced with x of t plus a delta x of t. The shift, this amount of shift, for example, this kind of shift, this is represented by a delta x of t, and this is tb and ta, and axis of t. All right, so I'd like to vary them. However, keeping the two endpoints the same, because we'd like to find the shortest path connecting A and B, we must not change the starting and end point. And we'd like to check how the length of the curve changes depending on the variation. That is our next problem. Now the x-axis is still the same. The point, 2 points are fixed, and x-axis are still the same. So everything is invariant. Instead, the integrand that was square root 1 plus x dot squared, that should be shifted due to the variation of the function x. Now, we assume this change is infinitesimal, very small, very tiny. Then the change in the integrand is a square root x dot plus the delta x dot squared subtracted by this original value. Okay, wait a second. All right. Now we know the variation of x is tiny. We can make an expansion with respect to the small parameter delta x. So, expansion formula for a plus the b squared is a squared plus 2ab plus b squared. And we know this delta x is tiny. All right. Then this is the original value. This is the original value. So we had better to pull out the original value for the square root, and then the expansion is a little bit simpler. Even if we have both the delta x and delta x squared that is smaller than this, we can assume the whole thing is a tiny value. And this is the right time to apply what we learned before. Newton's generalized binomial theorem can be applied to find expansion with respect to alpha that is tiny. So we have 1 plus alpha n, and n equals 1/2. So this is 1 plus n alpha plus n minus 1 over 2 alpha squared, and so on. So if I substitute 1/2 for this n, it is 1 plus alpha, and then so this is a minus 1/8 alpha squared and order alpha cube or higher. Therefore, a tedious calculation gives the result in powers of delta x dot. All right? Because we have this 1 plus x dot squared in the denominator of this whole alpha, we have a little bit complicated form. Anyway, this is what we obtained. Remember, what is delta L? So this one in here, we can pull this 1 plus x dot squared out, and we have square root 1 plus this one, okay, minus 1. And we have 1 plus x dot squared and 1 plus these, and subtracted by 1. So they cancel. And this is the contribution that we obtain for the variation of L. The L was 1 plus x dot squared, and the variation of x by delta x. So the integrand L changes by this amount. For simplicity, we first consider the leading contribution. That is first order delta x contribution is this. All right. So this is another right time to apply Leibniz rule. Okay, we remember variation x time derivative is just the variation's time derivative. Okay. And then we have x dot delta x dot. Why don't we compute this? This one, it's better to find the total time derivative of a, b equals a dot b plus ab dot. Therefore, a dot b equals a time derivative of ab subtracted by ab dot, something like that. Here, I can choose a equals delta x and b equals x dot over square root 1 plus x dot squared. So this is b and this is a. And what's that? This is b and time derivative of a. All right, so this is the time derivative a times b. Okay, this is the direct application of Leibniz rule. As a result, using this identity, we substitute this identity in here. Right? This is this. So this integral over t is replaced with this difference. We know this is the total time derivative. Total time derivative is integrated over time again. Therefore, the answer is integrand itself evaluated at the endpoint subtracted by another starting endpoint, the starting point. And we remember the variation delta x disappears at endpoints. Therefore, this contribution is nothing. The only contribution is this. What is this? What we have computed is the change in the length of the curve once we change the path by a small amount, delta x, as a function of time. As a result, this one is copied here. Now, we can say the first order correction to the length of the curve after varying the path from x is this. By the way, because s is the minimum value, why? Our question is that what is the shortest path connecting A and B? So we assume the original path represented by this x of t function is the minimum value, represent the minimum value for the path connecting A and B. Therefore, if it is a minimum, what we know is that whatever variation from this path, this or that, whatever variation from x of t, this variation must, this is function of x, and it becomes the minimum value when the first order derivative of this function is 0, minimum. Sure, if it is minimum, the second order derivative positive so that the slope increases from negative and reaches 0 and then positive. So that's the reason why whatever variation you may bring in, this integral must vanish at the minimum value of s. That is represented by the function. The path is represented by that function. Therefore, whatever delta x you may bring in, this should be 0. This has this unique solution that the derivative of x dot over square root 1 plus x dot squared must be 0. Okay, as a result, this is 0. Why don't we integrate over time? Then this one is a constant. A simple calculation shows that x dot squared is a constant. What is x dot? This is T connects A and B, and this x of t represents a curve, but the first order time derivative, that means first order this t derivative of this path is what? Constant. Constant. That means this one. The slope is constant, but we have chosen the two endpoints A and B along the x-axis. So that was the straight line on this straight line. So the curve should not be broken. They are connected, and slope is constant all the way from A to B. That means slope is just flat, and the curve connecting A and B is nothing but a straight line. Okay, so next we consider the second the contribution, because this derivative vanishing this constraint does not say this function f is a minimum. It is either minimum or maximum. The only way to check whether it is a minimum or a maximum is to compute the second order derivative. The second order derivative can be evaluated by making use of our previous result. This is the first order and this is the second order. The second order contribution is this, and we know square root is positive. Delta x dot squared, this is also positive. Square of a real number is always positive. Therefore, the second order correction to the length of the curve from the minimum value that is represented by the straight line connecting A and B is positive. Therefore, the line connecting A and B, the straight line connecting A and B, represent the curve that has the minimum distance from A to B. That's it for today. Thank you.